There is only one Anurag, I believe. This is a 21st lecture on convolution, modulation and other properties of discrete time Fourier transform. First we do the convolution property, and you recall that if in the continuous time domain, if y of t is the convolution of h of t and x of t, then the corresponding Fourier transform relation is y of omega equal to h of omega and x of omega. And you saw how important this relationship is in the analysis of linear time invariant system. In linear time invariant system, y of omega is the transform of the output, x of omega is the transform of the input, and h of omega is the so called frequency response. In the discrete time domain, an exactly similar relationship holds, that is, if we have an h of n describing a linear time invariant system and you convolve with x of n being the input and the output is y of n, in an exactly similar manner, except for the fact that integration is replaced by summation, the Fourier transform relationship is that it is simply the product of the two, h of omega and x of omega. I shall skip the proof because the proof is quite simple and mechanical. The interpretation is that if there is a system whose impulse response is h of n, or whose the Fourier transform of its impulse response is capital H of omega, which by analogy with the continuous time system is again known as the frequency response function. In general, it is a complex quantity, it has a magnitude and a phase, and x of omega is the spectrum or the Fourier transform of the input signal. Then the spectrum, the output signal is simply obtained as the product of the two. As I said, I shall skip the proof. Then we take the case of differencing. Now we cannot talk of differentiation in the time domain, because in the time domain it is a discrete case, and therefore all we can talk about is differencing. That is, if x of n is the pair of capital X of omega, then x of n minus x of n minus 1, the minimum difference is one sample. So this is a differencing. In a sense, this is the analogy of differential coefficient. It is xn minus xn minus 1 divided by 1, alright. It is a difference instead of a differentiation, and the Fourier transform of this shall be obviously capital X of omega, then 1 minus, for this the Fourier transform will be x of omega e to the minus j omega. So it is 1 minus e to the j omega. That is the relationship for differencing. You recall for reference that if in the continuous time case, if x of t is the Fourier transform is capital X of omega, then this implies that dx dt is the pair of j omega times capital X of omega. You see, multiplication by j omega now is replaced by a 1 minus e to the minus j capital omega, alright. Differencing makes this kind of a difference. That is, for continuous time domain it is a multiplication by j omega. In the discrete time domain it is still a multiplication, but the factor is 1 minus e to the minus j omega. When you go to the case of integration in the continuous time domain in CT signals, you recall that if x of t is capital X of omega, then integral minus infinity to t x of tau d tau is capital X of omega divided by j omega plus pi capital X of 0, that is the spectrum at DC, multiplied by delta of small omega, alright. delta of small omega. Now, what is the corresponding relationship? Obviously, it would be summation. In the discrete time system, in the discrete time signal, integration shall be replaced by summation. And let us see what the particular relationship is between the time domain summation and its spectrum. The the development is slightly involved. I had said this as a tutorial problem, but I think it is instructive to do it here. What we are trying to do is to find out the Fourier transform of capital X of n, where m goes from minus infinity to, let us say, n. It is similar to integral of x tau d tau from minus infinity to small t. It is this instant of time n that we are concerned with, and what we want to do is to find out the Fourier transform of this, given that the Fourier transform of x of n is equal to capital X of omega. That is what we want to do. One of the easy things that occurs to us is that if y of n, follow this carefully, if y of n is m equal to minus infinity to n, x of n, then obviously y of n minus y of n minus 1 is equal to x of n. Isn't that right? And if I take the Fourier transform on both sides, obviously capital Y of omega should be equal to capital X of omega divided by 1 minus e to the minus j omega. Alright, and therefore this relationship appears to be quite different from the corresponding relationship in the continuous time case. In the continuous time case, there was a delta omega, but then there is a subtle mistake that we have committed, and this result is indeed incorrect. The mistake is that in this relationship yn minus y of n minus 1 equal to x of n, suppose y of n has an average value, then this average value cancels out with the average value of y of n minus 1. At least there is a subtraction, and therefore when we are finding out capital Y of omega, which is the Fourier transform of y of n, we cannot take care of the average value if we find out y of n, if we find out capital Y of omega from this relationship. Is the point clear? No. Alright, let us illustrate this with the help of a unit step function. A unit step function in the discrete time domain is like this. It starts at 0, 1, 2, 3, 4, goes on, and on the left hand side it is all 0, minus 1, minus 2, minus 3, and so on. Now, what is the average value of this function? Obviously, the average value is half. Okay, average value is half, and therefore u of n, I am taking an example, then I shall go back to y of n, the general case. Therefore, you can write u of n as some u bar of n plus half, some other function u bar of n, where the average value of u bar of n is equal to 0. Alright, u of n can be written like this. Now therefore, the Fourier transform of u of n is equal to the Fourier transform of u bar of n plus the Fourier transform of half. Alright, so if we know the Fourier transform of u bar of n, whose average value is 0, then we can find out the Fourier transform of u of n. On the other hand, we know that the Fourier transform of delta n is equal to 1, and delta n can be written as u of n minus u of n minus 1, right? Now, in this relationship, obviously, the average value of u of n is cancelled out. Average value of u of n is half, average value of u of n minus 1 is also half, and therefore things will not change if we put a bar over this. Isn't that right? The average value of u bar of n is 0, and since the average value cancels out, if u is replaced by u bar, it doesn't make a difference, which means that the Fourier transform, well, we write delta n as u bar n minus u bar n minus 1, and therefore 1 if I now take the Fourier transform. There is no question of average value because the average value of u bar is 0. So it would be the Fourier transform of u bar of n multiplied by 1 minus e to the minus j omega, and therefore it would be quite correct to say that a Fourier transform of u bar of n is equal to 1 by 1 minus e to the minus j omega. This is quite correct because no average value has been cancelled out. If we now go back to the original function, what was the original function? It was f of u of n was equal to f of u bar of n plus f of half. Okay, if we now go back to this, obviously what we see is 1 minus e to the minus j omega plus f of half. Now the Fourier transform of a constant, that's all that we are lacking now. And why does this term arise? Because it takes care of the average value of the function. We cannot find out the Fourier transform of a function from a difference equation, because in a difference equation the average value may be lost or may be distorted. Alright, it is not necessary that the average value of y of n and the average value of y of n minus 1 are the same. It is not necessary, isn't that right? The average value shall be distorted, and therefore we cannot find out the Fourier transform of a given signal y of n from a difference equation satisfied by it. Alright, we have to go back, we have to take care of the average value. Now if I consider this, all that I need now, f of u of n, all that I need now is 1 minus e to the minus j omega plus the Fourier transform of half. Now you recall that the Fourier transform of e to the j n omega 0 is, this is a time domain signal, e to the j n omega 0. What is the Fourier transform of this? This is a sequence. It is a summation twice pi summation delta of omega minus omega naught minus 2 pi L, as complicated as that. In the continuous case, e to the j omega 0 t, the Fourier transform was simply delta of omega minus omega 0, whereas here it is a chain of delta functions, and these delta functions are the arrowed delta functions. These are not discrete, these are continuous omega, capital omega domain delta functions. L goes from minus infinity to plus infinity. The only difference between e to the j n omega 0 and half is that omega 0 is equal to 0, and therefore the Fourier transform of u of n, now if we are bold enough to write this as capital U of capital omega, all bold, is equal to 1 by 1 minus e to the minus j omega plus, there is a factor of half, half and 2 cancel, so plus pi times summation L equal to minus infinity to plus infinity delta of omega minus 2 pi L. This finally is the Fourier transform of a unit step function. And you notice the difference. The difference is that in the continuous time case, u of small omega, if I write it down, u of small omega was 1 by j omega plus 2 pi and then simply delta omega. Now if you compare this, capital U of capital omega, j omega is replaced by 1 minus e to the minus j omega. This we saw in the differencing case also. It's the same factor plus twice pi, instead of a single delta function, we have delta of capital omega minus 2 pi L, L equals minus infinity to plus infinity. Pardon me? It is only pi. Thank you. It is only pi. Alright. You must, in the first case also, quite correct. This 2 is not there. Alright. Thank you. Now you must be able to recall these two expressions, because unit step function is a very, very important function. Now we shall utilize, as in the continuous time case, we shall utilize this result for finding out the Fourier transform of the summation of x of m from m equal to minus infinity to n. The quantity, we wanted to find out the Fourier transform of a summation, exactly like we found out the Fourier transform of an integration. Now the quantity within the square brackets can be written as summation x of m. Suppose we write u of n minus m, alright. Then m goes from minus infinity. What is the upper limit of n now? M. It can go to plus infinity. Isn't that right? Aren't these two summations the same? Because u of n minus m is 0 if m is greater than n, and therefore virtually it is the same thing as this summation with upper limit replaced by n. Usually we go from here to here, usually in our usual calculations. It's for convenience we now go from here to here, and you notice that this is simply the Fourier transform of the convolution of x of n with u of n, and therefore we apply the convolution theorem. The convolution theorem says that the Fourier transform of if we say y of n is equal to summation x of m, m equal to minus infinity to n, then this can be written as convolution of x of n and u of n, and therefore capital Y of omega, which is the Fourier transform of this summation, should be simply equal to capital X of omega multiplied by u of omega, which we have just proved as 1 by 1 minus e to the j omega plus pi summation delta omega minus 2 pi L. L goes from minus infinity to plus infinity. Now let's multiply this out. We get capital X of omega divided by 1 minus e to the minus j omega plus pi. Now the question of capital X of omega evaluated at each of these values, that omega equal to 2 pi L, where L goes from minus infinity to plus infinity. Alright. Now what is the difference between these values? You see, for an L equal to 0, the value is capital X of 0. When L equal to 1, the value is capital X of 2 pi. When L equal to minus 1, capital X of minus 2 pi. What is the difference between these values? Identical, because capital X of omega is periodic in omega with a period of twice pi, and therefore I can simply use capital X of 0, alright, instead of all these values, and then summation L equal to minus infinity to plus infinity delta of omega minus 2 pi L. This is my final result, that is summation x of m, m equal to minus infinity to n. The Fourier transform is this. This is my final result and we shall depend on it, we shall bank on it for many of our developments. Alright, so that takes care of differencing and summation. We had started a discussion on time compression and time stretching last time. We want to take this discussion to its natural conclusion, that is you remember that in the continuous time domain, if we have x of t as the pair of capital X of small omega, then x of a t, and depending on the value of a, it can be time stretching or time compression. The Fourier transform is 1 by mod a capital X of omega by a. So if it is stretching in the time domain, it will be compression in the frequency domain. If it is compression in the time domain, it will be stretching in the frequency domain. And this is the business of duality that we dwelt upon in a little more details earlier. In the discrete time domain, there is nothing called stretching, because in the discrete time domain, if x of n is the transform, let me use a different color. If x of n is the transform of the transforms into capital X of omega, then x of a n does not have a meaning unless a is an integer, and therefore this property cannot be brought into the discrete time domain in toto. There must be some modification, because x of a n is meaningless unless a is an integer. Also, I discussed that x of 2n, for example, even if a is an integer, x of 2n is not a compression of the original signal. It is a distorted signal. It is a sampled version of the discrete time signal. It only takes the even values, and therefore it is not a case of stretching. I am sorry, it is not a case of compression. All right. So we have to modify this definition a little bit, definition of stretching and compression, and to that end we define a sequence. Suppose we have a sequence x of n, then we define a sequence x of k n, k a subscript within a bracket. We define this as x of n by k if n is an integer. No, I beg your pardon. If n is n of course has to be an integer. If n is a multiple of k, that is, n could be 0, n could be equal to k, n could be equal to twice k, n could be equal to thrice k, and so on and so forth. All right. If n is a multiple of k, then it is x of n by k, it is 0 otherwise. This sequence has a lot of applications in communications, and therefore this is a derived sequence. You see, this is a sequence derived from x of n. X of n is the pair of capital X of omega. Then what you have to find out is x of k of omega, and we will see that the concepts of stretching and compression do occur here if you define a signal like this. Well, there is no other definition that you can give, because x of a n does have no meaning unless a is an integer, and therefore it is only at integer values. Now, what does this definition do to a given signal? To see that, let us consider a specific example. Let us say we have a signal like this, n 0, 1, 2. No, I have put a 0 already. Okay. What we do is, let us say this is 0, this is 1. Now, let us take a 0 also somewhere here. 1. Let us say this is 2, 3, and let us say 4 is somewhere here. Let us take a negative value. 4. Let us say 5 is like this, and 6 is here. Let us consider a signal like this. All others are 0. Just an example, all right. This is my x of n. And for simplicity, suppose k equals to 3. Then what I want to find out is x k of n. what shall it look like? This is what I want to see. At 0, at k equal to 0, the signal is the same, that is, it is this signal. At k equal to 0, if you recall, x k of n is equal to x of n by k, n divided by k. So, if n is 0, it is the same. When n equal to 1, x of n by k, k is 3. So, when n equal to 1, by definition the signal is 0. When n equal to 2, again the signal is 0. When n equal to 3, what we get is x of 1, and therefore my signal, I am sorry, it would be like this. Okay, this is 0, 1, 2, 3. Alright. So, 0 comes here, 1 comes not at 1 but at 3. Similarly, 2 will come at 6, and therefore 4 and 5 they shall be 0. At 6 we shall have this. You see what is happening? The signal is stretched. The signal is stretched, but the voids or the empty ones are filled by zeros, zero valued samples. Okay, so this is in a sense a stretching of a signal. Let's see what happens in the frequency domain. All right, for the same case, what I have is x of 3 of n was at 0 it was x of 1, then 0, then 0. At 3 it was, I made a mistake, at 0 it is x of 0, at 3 it is, the value is x of 1. I am writing it in a slightly different manner now. I am writing the values in terms of the original sequence, that is x of n. Then 4 is 0, 5 is 0, at 6 the value is x of 2, and so on. Now, if I find out the Fourier transform of this, what do I get? X of 3 of omega becomes equal to x of 0 plus x of 1 e to the minus j, yes, the value is x of 1, but where does it occur? At 3, so minus 3 omega. The next one, the value is x of 2, but it occurs at 6, so e to the minus j 6 omega, and so on. Don't you see, if you compare this with the definition of capital X of omega, what is capital X of omega? It is x of 0 plus x of 1 e to the minus j omega plus x of 2 e to the minus j 2 omega, and so on. If you compare this with this, don't you see that this is simply capital X of what? 3 omega. So there was a stretching in the time domain, a stretching with voids filled up with zeros. Now there is a compression in the frequency domain, all right, which is exactly the reflection of duality between the two domains. That is, if there is a stretching in the time domain, stretching in the discrete time case has to be defined appropriately, because otherwise x of an does not have a meaning unless a is an integer. This is the basic issue, and therefore we had to define x k of n. We had to define a k, x k of n, and then the spectrum became compressed. It can be shown that the converse is also true, but you have to be very careful. We will come to this when the need arises. But in general, if you define an x k of n as equal to x of n by k, n equal to kr, r integer including 0 and is 0 otherwise, if you define a signal like this, then obviously x k of omega would be simply capital X of small k multiplied by omega. We had illustrated this for k equal to 3. In general, this will be the relationship. that takes care of stretching and compression. The next property concerns the energy. In other words, it concerns what we have mentioned again and again, the Parseval's theorem. The proof is exactly similar to the continuous time case. You remember, in the continuous time case, the energy in the time domain, this was minus infinity to plus infinity excuse me, xt mod square dt, and in the frequency domain the energy was integral minus infinity to infinity capital X of omega, then mod squared, right, d omega divided by 2 pi. And then under this condition, just for recalling sake, X of omega squared was given the name of energy per unit which frequency, angular or linear? Hertz, because d omega, it's in radians, radians divided by 2 pi is hertz or cycles per second. So this was called the energy density spectrum, energy density spectrum. It has the dimension of energy density, energy per unit hertz. In the discrete time case, a similar relationship holds good. Instead of an integration, we shall have a summation, and obviously this shall be x of n squared over all values of n, alright, x of n squared over all values of n, and this should be equal to, now the integration cannot be from minus infinity to plus infinity, because capital X of omega is periodic, and therefore it is 1 over 2 pi integral over one period, capital X of omega mod squared d omega. This is all the difference. The left side is the energy in the time domain, and the right side is the energy in the frequency domain, alright, over one period. This is the difference. This difference arises because capital X of omega is periodic. Now what kind of a signal will this relation apply to? Obviously the signal has to be an energy signal, because the left hand side is the energy in the time domain. If this energy goes to infinity, the Fourier transform may or may not exist. This is one of the sufficient conditions, that the energy should be finite. So for finite energy signals are known as energy signals. Finite energy signals, the Parseval's relation is this. On the other hand, if it is a power signal, what is a power signal? Energy goes to infinity, but the power, energy per unit time is finite. For a power signal, of which the periodic signal is an example, for a power signal, what is the relationship? Obviously the relationship shall be if we take a periodic signal, it would be over one period, that is n, if the period is capital N, over one period. This is the energy over one period. If we sum it up for all periods, obviously it will go to infinity. If you want the power, then you have to divide by the period. So this is the power in one period of a periodic signal, and this shall be equal to, now will the integral relationship come or something else will come? Summation of the Fourier coefficient magnitude squared, that is ak squared. Now what is the number of terms? Number of terms is n. Once again this summation is over one period, because the Fourier series is periodic. That doesn't make sense. Fourier series is finite. The function is periodic, Fourier series is finite, and therefore all you have to do is this. And the proofs are extremely simple. All that you have to do is to slog through a little bit of mathematics and flip over these summations, all right. That is all that you have to do. You have to identify two independent variables and then make one summation first and then the other summation. Enough of theory, let us work out some examples. The first example that we take is that of a system, a linear time invariant system described by h of n. This is x of n, a trivial example, and this is y of n. And h of n, let us say, is equal to delta n, all right. Then what is y of n? What is the relationship between y and x? Y equal to x. So what do we call this system? Identity system, all right. You notice that if we transform to the frequency domain, then capital H of omega is equal to 1, and therefore capital X of omega and capital Y of omega are the same, because the relationship between capital Y, capital H and capital X is that capital Y is equal to capital H times capital X, all right. Now suppose we change this. Suppose it's a delayed impulse. Suppose h of n is equal to delta n minus n0. Then what is my y of n? That's right. It is simply delayed, and if you look at this relationship in the frequency domain, capital Y of omega shall be equal to capital H of omega, which shall be e to the minus j n0 omega multiplied by capital X of omega. And if you take the inverse transform of this relationship, then you precisely get this, y of n equal to x of n minus n0. We had proved it in the forward direction, that is, if a signal is delayed, then the Fourier transform is multiplied by e to the minus j number of samples by which it is delayed multiplied by omega, e to the minus j n0 omega. Okay, let us go to a more complicated example. It is the same type of example that we did in the continuous time case. H of n is alpha to the n a n, and x of n is of a similar form, beta to the n u n, beta to the n u n. Then y of n, which is the convolution of x of n with h of n. Does it matter whether I write x or h first? No, it doesn't, because it is commutative operation. Then capital Y of omega, obviously we know the Fourier transform of this. It is 1 minus yes, e to the minus, is that right? No, alpha multiplied by alpha, and this shall be multiplied by 1 minus beta e to the minus j omega. And all we have to do now is to take the inverse transform of this, and we apply the same kind of trick, that is, we write this as a divided by 1 minus alpha e to the minus j omega plus b divided by 1 minus beta e to the minus j omega. Find out a and b and then invert term by term. One can easily show that, let me write this again, y of omega is 1 by 1 minus alpha e to the minus j omega, 1 minus beta e to the minus j omega, and this is equal to a divided by 1 minus alpha e to the minus j omega plus b divided by 1 minus beta e to the minus j omega. To find out a and b, we can apply different techniques. We can take the numerator a times this plus b times this and equate to 1, or we can multiply by 1 minus alpha e to the j omega, both sides. If I do that, a, for example, is 1 minus alpha e to the j omega multiplied by y omega under the condition that what is it? alpha is equal to e to the j omega, or e to the j omega equal to alpha. Now if I do that, if I multiply this by 1 minus alpha, then obviously what we get is 1 by 1 minus beta divided by alpha, right? If I multiply this by 1 minus alpha e to the j omega, this cancels out, then 1 minus beta times e to the minus j omega, but e to the j omega is alpha, so e to the minus j omega is 1 by alpha. That is, this is equal to alpha divided by alpha minus beta. In a similar manner, you can show that b is equal to, can you tell me what b is? Beta divided by, that is right, that is minus alpha minus beta. Okay. So we go back to the original equation. Y of omega is equal to 1 by alpha minus beta, then you get alpha divided by 1 minus alpha e to the minus j omega minus beta divided by 1 minus beta e to the minus j omega. And now we can invert it term by term, that is, we get 1 y of n is equal to alpha minus beta then what is the inversion of this? Alpha to the n plus 1. Where does it plus 1 come from? Alpha. So it is u of n minus beta to the power n plus 1 u of n. And obviously for this to be valid, alpha cannot be equal to beta. Now what do you do if alpha is equal to beta? You go back to the original function. That is, if alpha equals to beta, then y of omega shall be equal to 1 by 1 minus alpha e to the minus j omega whole squared. And here, to be able to evaluate this, we require what happens when we differentiate the spectrum with respect to omega. What happens to the time domain? We require that expression. If I look at x of n is the pair of capital X of omega, we are doing ab initio. We could draw a parallel between this and the continuous time domain, but we are not assuming this. We will do it right from beginning, because it is extremely important to understand this. There are some subtleties in this which I want to explain while doing this. Capital X of omega by definition is x of n e to the minus j n omega, with appropriate limits of n equal to minus infinity to plus infinity. And therefore, if I differentiate dx d omega, then this would be equal to minus j n x n e to the minus j n omega, n equals to minus infinity to plus infinity, which shows that dx d omega must be the Fourier transform of this new sequence minus j n x n. All right. So is that okay? Therefore, we write this valuable relationship, that is, if x n and capital X of omega are pairs, then dx d omega is the pair of minus j n x n. Now, if I want to show a real sequence, if I don't want to show minus j here, then what I do is I take this out and divide by minus j, in other words multiply this by j. This is the relationship, that is, j dx d omega is the Fourier transform of n times x of n. Now our problem was to find out 1 minus alpha e to the minus j omega whole squared. Our problem was to find out y of n whose transform is this. And we start from x of n. We know that 1 by 1 minus alpha e to the minus j omega, this is the Fourier transform of alpha to the n u of n. Now if I multiply this by n, alright, if I multiply the left hand side by n, then by this relationship we should multiply this by j and take d omega of this. Alright, let's carry this out and see what the result becomes. N times alpha n un, the Fourier transform is j. Now d omega of 1 by 1 minus alpha e to the minus j omega, this I can write as j minus 1 divided by, let's do it carefully, 1 minus alpha e to the j omega whole squared, alright. Then differentiation of this with respect to omega, so we shall get minus alpha, then minus j e to the minus j omega, alright. There are many things that have to be taken care of. Let us see what these are. J and minus j shall become plus 1, and minus 1 and minus alpha shall become plus alpha, and therefore what we have is alpha e to the minus j omega divided by 1 minus alpha e to the minus j omega whole squared. This is the Fourier transform of n alpha to the n u of n. We have not yet achieved our result. We don't want anything in the numerator. We don't want a 1. We want a 1, and therefore what we do is first we divide by alpha. First we divide by alpha. So this becomes alpha to the n minus 1. Then to take care of this e to the minus j omega factor, we multiply by e to the j omega. What happens to the left hand side? N should be changed to n plus 1. We are multiplying by e to the j omega. If we multiply by e to the minus j omega, then n should be changed to n minus 1. Now we are multiplying by e to the plus j omega, and therefore n should be changed to n plus 1. That means what we get is n plus 1 alpha to the n u of n plus 1, alright. This would be the transform of 1 by 1 minus alpha e to the minus j omega whole squared, and therefore, is it okay? Therefore our desired y of n would be equal to, desired y of n would be equal to n plus 1 alpha to the n u of n plus 1, which I can write as n plus 1 alpha to the n un. Would you agree? Or not? Yes, because at n equal to minus 1, this term gives it 0, and therefore this is my final result. Y of n equals to n plus 1 alpha to the n un.
You can get this straight away from that result. You can factor out alpha minus beta. You got the result alpha to the power n plus 1 minus beta to the power n plus 1.
Yes. Let's go back. That's a very interesting point. Let's go back and see if we could get it. What he's saying is, why do you go through all this trouble? Why don't you take the previous expression when alpha was not equal to beta? Is that what you are saying? Okay. It is 1 by, was it alpha minus beta or beta minus alpha? Alpha minus beta. Then alpha n plus 1 minus beta n plus 1 u of n. Alright, now what are you saying?
You factor it out, you get alpha n plus alpha to the power n minus 1 beta plus so on till beta n. Put beta equal to alpha, you will get n plus 1 times alpha.
Yeah. You could get it from here also. You see, for example, if n equal to 1, then this is alpha squared minus beta squared, which is alpha minus beta as a factor. Any power of here, alpha to the n plus 1 minus beta to the n plus 1 has a factor of alpha minus beta, which shall cancel out, and the rest that is left behind would be,
there will be n plus 1 term. So, but we can't cancel it out, sir, when alpha is equal to beta. We take the limit.
take the limit. Take the limit as alpha tending to beta. We can do this by L'Hopital's rule also. It's the same thing. Well, from this to go to alpha equal to beta is a limiting process, and in the other derivation we have not assumed any limiting process. The results are the same and both results are correct. Both procedures are also correct. Finally, we talk about the modulation property. That is, if y of n is x1 of n multiplied by x2 of n, in the continuous time case you saw that if a signal is the product of two time signals, then the Fourier transform is the convolution of the two spectra. This is exactly so in the discrete time case also, and what happens is y of omega is simply x1 of omega convolved with x2 of omega, and it is extremely simple to prove this because capital Y of omega is.
But these are periodic. Won't that cause problems?
What is periodic? Both x1 and x2 are periodic. That is correct. So y of omega shall also be periodic.
So, but that won't be defined then. We'll take convolution over a period.
We will take convolution over one period. Because the convolution shall also repeat. Because y of omega is periodic, it makes sense only to take the find y of omega in one period. And the proof itself shows how it is so. Y of omega by definition is x1 of n, x2 of n, e to the minus j n omega, n equal to minus infinity to plus infinity. What we do in this is that one of them, x1 of n for example, we replace by its inverse Fourier transform relationship. That is 1 by 2 pi integral over 2 pi capital x1 of since omega occurs here, let's take a theta. After all, it's a dummy variable, isn't it? So x1 of theta, then e to the power j, yes, n theta d theta. This is by x1 of n. And then I have x2 of n e to the minus j n omega. Let me indicate what is to be done now rather than carrying out these steps. What I do is I take the integral out and first make the summation. The summation over n. Summation over n shall contain this term x2 of n, shall contain this term e to the minus j n omega, and also this term e to the j n theta. There is no other term containing n. And what I can write here, if you combine these two, then you get e to the minus j n omega minus theta. Alright, so x2 of n e to the minus j n omega minus theta, the summation from n equal to minus infinity to plus infinity obviously gives you x2 of omega minus theta. So what you have in the integral sign is 1 by 2 pi integral over 2 pi 1 by 2 pi integral over 2 pi x1 of theta x2 of omega minus theta d theta, and obviously this is a convolution of x1 of omega with x2 of omega over one period. 1 over 2 pi is a factor which you must not lose sight of. Yes, that is correct. We shall take examples of modulation. This is a convolution of the frequency domain, and the name that is given to this property is the modulation property. We will take examples of this, interesting examples, in next time.